So we are back on this one. Alright, I'm just going to continue. Oh, that noise. Let me just. Okay, so like I was saying, this is the week I'm continuing with one of my learning Go tutorials online. So I'll just be doing my best to. Okay, so this is me. I was just trying to check out some projects. Cool. Now I'm just going to continue on what I was doing with GOLang. I was learning with Go, doing some tutorials on it. And if I go back to the repo, seems like I closed the pages. No, okay. So I was reading on constants, like how do you create a constant in Go, and this is what I was doing. And I quite recall, like from the previous one, there was not something like an audio that you could use. So I think I'm basically done with this constant. So this is something I needed to check. Using this symbol, it's actually it's like shifting, create a huge number by shifting a 1 bit by left, a 1 bit left 100 places. In other words, the binary number that is 1 followed by 100 zeros. Whoa. So binary number, so 1 in binary is 001. So if we are shifting it by we say shift to the left. Okay, we're shifting to the left. So by shifting a 1 bit left, shifting a 1 bit left 100 places. In other words, a binary number that is 1 followed by 100 zeros. So like here, we're just pumping in zeros like this. And then if we are shifting this now to the right by shift to the right again 99 places, so we end up with 1 or 2. Okay, so if we do like this, if we give it back like 99 zeros to the back, this is still generally 2, because 2 in binary is basically 0010. Yeah, so I guess that's what it's trying to mean. Okay, so we can leave that there. So numeric constants are high position values, and untyped constant takes the type needed by its context. Try printing need big into. An int can store a maximum of 64-bit integers and sometimes less. Okay, so let's run it and see what happens. So it runs the first function need int, which is x and int, and it returns the factor of x multiplied by 10 plus 1. So obviously x here in this case was small, and what was small was a bit shift by 2 places, which would be 2 times 10, which will give us 20 plus 1, we have 21. That one's obviously clear. Now we need a float, the small, which is 0.2. How did we get 0.2? So the small passing on another small constant, okay, small, which is big shifted by 99 pages, which is still the same 2. Now it's actually taking 2 times 0.1, which is 0.2. But now if we do need float now with the big, which was basically 1, and was it basically 1? No, wait, yeah, it was 1. We're multiplying it times 1. Okay, so it's a float, so we need float. A float 64 times a big, and big here in this case is this. So is this bit shifted by 100 zeros. So that's basically shifting 1, 2, 3, 4. I don't understand this one. Print need float big. Like, let me see what is the value when we print fmt print we're just printing big. What happens when we print that? Untyped int constant. And how is that sheet untyped? Ah, but how is it possible that they're using it as out of a function, but I'm trying to run the same instruction and I'm getting an error? So we have big equals 1 greater than that. We are shifting it by 99 places. Yeah, I'm not, it's not giving in my head. Okay. So actually this is the use of this symbol. It's just to do that. But a print big untyped in constant as, okay, there was already another part which as int value in argument everything over. Oh, okay. So this overflows. Makes sense. So this overflows. So let's say if I put here 5 to shift it by 5 places, it's supposed to print it out clearly. Yeah, that explains a lot. So if I put 5 here, so put that's 20. Is 20 supposed to create a memory overlay? I don't think so. Perfect. But if I were to do 64, I think 64 should be the maximum to shift it 64 places. Yeah, let's say 63. Normally it's a 32-bit signed integer that usually is the maximum, so 64 bits, so I think 32 is the maximum. Yeah, because this is 4.2, this is 32. From 33 there should be an error. Really? Then where does it actually stop? So it doesn't matter, it's just the number of zeros I'm shifting ahead. Okay, so we have 8, 5, 8, 9, 9, 9, 9, 9. So when you shift a number to the left by 100 places, when we shifted it to the right, we got a 2. By shifting it 100 places and multiplying that by the factor of 0.01. So this actually gives us an arbitrary value. But I think this also converts. Does it convert it? So let me see. An untyped constant takes the type needed by its context. Okay. By the type needed by its context. So context really matters. So if I said this big here was 100 and then need float, let's say I did float 64 and I pushed it inside of this big, what could be a result? Aha. Yeah, I get it now. I get it. So create a huge number by shifting one bit by left places. So numeric constants are high precision values. I think this is really useful for system programming. Yeah, really important for system programming, because I think it's there where, you know, like you kind of really need to take into consideration all of those to be very precise when shifting binaries. I don't know much about this because I'm still learning data structures and algorithms, so I'm still doing some tryouts there, so most likely I'll look up into it. So we have finished the lesson. Okay. I think wasn't this the tour guide? Nah. Okay, so this one has to do with for loops. Go has only one looping construct, which is the for, so it doesn't have a while loop. Yeah. Round of applause, Go developers. Round of applause. Yeah. Some of us are coming from the backgrounds using while loops, yeah. So it's good they don't have. It's good they don't have support for while loops. So the basic for loop has three components separated by semicolons. The init statement executed before the first iteration. Really? Executed before the first iteration? What's that supposed to mean? The condition expression evaluated before the iteration. Okay, yeah, sure. The post statement executed at the end of every iteration. Okay, so sums it up just like regular. So this is just like, I think it's like regular normal C#, C++. But in this case, which language is similar in terms of syntax to this? I think this is C. Yeah, this is very similar to C. I think JavaScript too. But I think the only difference with this is with JavaScript is somehow put like some parentheses here, like that, and having this already gives you JavaScript, except for this signature move from this. I think I've forgotten how they call this. I think Python also supports this. Wait. Yeah, assignment operator, but I think it is a name it's given to it. Short variable declaration operator. Nah, that name sounds whack. I'm sticking with assignment operators. Jesus, didn't know that name was kind of whack. Yeah, for loop. Okay, so let me create my own for loop. So for let me remove this before I get weird syntax errors issues. So I wanted to do, say I, let's do the reverse. So I is equals to, I'd say 100, and I is less than 10. I is lesser than 0. Right, we're going to do I minus, and then we're just going to do a sum plus, oh wait, why did they need to do sum plus equal to 1? Okay, because they are like doing the subtraction over there. Sum, we're just going to do, yeah, plus equal to 1 plus I. So what I'm guessing is 100 here will be added on top of I, so you have 100. The next iteration, 100 plus 0. The next one you have the initial 100 plus the next value will be 99, which will give us 199. So FMT at the bottom here, we want to just print line and the sum. Let's run. 45. So why is this stuff still 45? Let me move this one. Run. Answer is 0. Why? Empty. Dot print online sum. So let me print that sum and see. You know, I was actually saying it was similar to JavaScript or C without even reading this. Yeah, true story. Is it that there is no I minus minus supported here, or I'm just getting confused? Weeping profusely. Let's run this. It's printing out 45. So you have sum plus equals to 1, you have 10 plus 9, 9 plus 8, 8 plus 7, 7 plus 6, 6 plus 5, 5 plus 4, 4 plus 3, 3 plus 2, 2 plus 1 should give you 45. Isn't it? What I don't get here is how is it possible that I'm calling in run this nonsense. Good, so definitely 0. Oh, it starts from 0, so it's 0 to 1, 1 plus 2, 3, 3 plus 3, you have 6, 6 plus 4, you have 10, you have 5 plus 10, you have 15, they have 6 plus 6, yeah, 5 plus 10, you have 15, then that will be 15, you have now 15 plus 6 will give you 21, and so on till we get to 45. Okay, what is happening when I do minus minus? I should have infinite loop. Yeah, that's why it asked me to queue. So you obviously want to an infinite loop, right? Which is basic. Yeah, timeout. Yeah, it just bloated the servers. Wow, that shit was fast. Okay, a good way to kill your computer, yeah? So this should be like 10. And this should be like 0. I equals to 10 when I is lesser than 0. Is I lesser than 0? Oh, that's why the condition wasn't working. I have to say I is actually greater than 0 until the condition turns false. Wow, what a rookie mistake. Now we're getting there finally. So different response here. So if I wanted to describe what was happening here, I'll actually do this and the answer should be 0. Minus 55. Why? I is 10. I is greater than 0 for sure. I minus minus. So we're taking the sum, we subtract it by I. So sum equals sum minus I. What's with the initial sum? 0, 0 minus 1, 1. Okay, yeah. Everything will be going to the negative direction, obviously. Okay. Got 4 loops. 4 continue. The init and post statements are optional. Oh, 4. So this is typically our normal while loop. So we can just say sum lesser than 1000, sum plus equal to 1024. Okay. But what happens inside here? Is it that this thing runs infinitely, or what makes it stop? So let me fmt.print and then 2, 4, 8, 16, 1024. Okay, so it continue working as long as the condition is is true. Okay, cool. For its goals, what at that point you can drop the semicolon. C's while is spelled for in Go. Sure. Pretty dang obvious, like I just said. Wow, that is quite a feature. Cool. goes if statements. I think I've worked with this like when I was working with modules. Yeah, I think I work with some if statements here. I think the syntax is pretty basic, like condition, at least here, no brackets, no semicolons. I like that. If with a short statement, like for the if statement can start with a short statement to execute before the condition. Ah, okay, like you assign a variable to this and then you're comparing v against this. Okay, so that's possible. Okay, I'm used to with this in Python. You can do this also in Python too. If an else block, yeah, let me see this. Print power, so like power of a number. So 27 is greater than or equal to 20. And all of them will float 64 numbers. 9 and 20. Okay, that's obvious. Exercise loops and functions. As a way to play with functions and loops, let's implement a square root function. Given a number x, we want to find the number z for which z squared is most nearly x. Computers typically compute the square root of x using a loop, starting with some guess z. We can adjust z based on how close z squared is to x. Producing a better guess. Repeating this adjustment makes the guess better and better until you reach an answer that is as close to the actual square root as you can be. And also notice this doesn't say square, it's asking a square root of a number. Okay, so implement this function in the func square root provided a decent starting guess of z is 1. Now cover the input to begin. Repeat the calculation 10 times and preach each z along the way. See how close you get to the answer for various values of 1, 2, 3 and how quickly the guess improves. Int. Okay, so the function to get the square root of a number. Okay, so what's the square root of 2? Square root of 4 is 2. this is something I've never actually tried implementing. So this is what they are basically saying. So we are trying to get the square root of a number, and to get the square root of a number, we'll run a loop 10 times. That would, and that would, in fact, let me just instantiate z. So we have z like that. Instantiate it as 1.0, and then we have like that. We can either instantiate it like that, or we just call the float64 method, and then we call 1 inside. Then what we're going to do is going to run a for loop, and we're going to say for z, so we're adding like 1.0. Can adjust z based on how close z squared is to x, producing a better guess. So z minus equals to z times z. Okay. Yep. While z yz is lesser than 10, 10.0. Yep. We're going to do z plus plus. Oh, this should be I. Okay, this should be I. And I is lesser than 10. We'll do z I plus plus. Now inside we want to do z with plus equal to, or you have something like z times z minus x, because all the float 64 values, most definitely, divided by 2 times z, like that. Put this also in brackets. Okay, so definitely square root is just how many times that number squared is closer to x. Okay, so I think this is it. And they said we should print our z, so fmt.print line, I want to print out z. So let's print out how close our number is to z. So let's print out z and x. So print out x first, then we say, and then we print out z. Good. And then we can finally print our final z. fmt.print line, we have now z. I think that's it. So I plus plus. Let's run. I'm missing a return statement. Okay, so I think it's return, just return z. Run. So for the square root of 2, we have 1.25, 1.0.4 minus 0.628 minus 2 minus minus minus. I think, do I have the correct answer? No. Yeah, I used to hear of Newton's method. I studied this in school. This exponential would typically be a better approximation to the original function's root than first guess, and the method can be iterated. If the tangent line to the curve f of x at x equals xn intersects the axis at x of n plus 1, then the slope f x of n equals to f of x of n minus 0 divided by x of n minus x of n plus 1. Okay. Let's all pretend that we understood, right? Sorry for the noises. So you have next change to loop start once. Okay, to better understand this, let me open up the calculator here. Google should have one. So if we do the square, oh hell no, the square root of 2, we have 1.41421356237. Let's bring that guy over here. And what did we have? 4. Like, I'm not even close. Z times Z. And what's our initial value of Z? Ah, I'm doing this wrong. I'm not even using I. Yep, so this should not be here. I should be moving with this right about here. Wipe this bad boy here. I will do Z is lesser than 10.0. Z plus plus. Run this bad boy. Undefined Z. Yeah. I can return Z. Neither can I print this. Just to return. equals 64 1, and what did we just do? We just we are just doing a u plus assignment operator. Now we just do a u plus equals z, and then return u. Run this bad boy. Jesus Christ. Okay, let's take things step by step. Let me go back to the Wikipedia. I think I'm going to watch a YouTube video about I really need to understand how to implement this algorithm so I fully understand what it is I'm doing. You get me? So let's go to YouTube and just search for Newton's method. Organic chemistry tutor, my guy.
In this lesson, we're going to focus on Newton's method zeros of a function. So let's say if we have this function, f of x.
So I'm kind of like going to reduce my mic so that the sound from the desktop audio will transmit more clear.
Plus 1. Now there could be at least 3 solutions to this equation. We're going to focus on finding just one of them. So we have to guess a value for x. We have to pick a value to start with.
I think this is something I can do. What I think is square root using Newton's square root. Yeah, using Newton's method. I think that's what I should look for. Let me read here. Listen.
Newton's method is a fast way of getting square roots. It is a generalization of the Newton-Raphson method, which is jointly credited to Sir Isaac Newton and Joseph Raphson. Newton is famous for his contributions to astronomy, chemistry, alchemy, prisms, gravity, calculus, laws of motion, binomial theorem, and of course, riches on coins. Joseph Raphson is best known for his contributions to the Newton-Raphson method. This method works by approximating the square root and then iterating until the solution is good enough. And given the fact that the number of accurate digits in the square root solution doubles every step of the iteration, the good enough is usually very soon. This will make more sense with an example. This is the equation we have for getting the square root. Let's say that we want to find the square root of 3. Here, the a variable becomes 3, and that will remain unchanged for every iteration. Now we need to pick a number that will be our starting approximate answer. We can estimate or just make a flat-out guess. It doesn't really matter. A closer estimate will converge faster, but even one wildly off will still get there. Since we're going for the square root of 3, we'll guess that the answer is 2. 2 becomes the xn in this equation. Really, it's x0 because this is a 0th iteration. Now we solve for xn plus 1. And that is the average of 2 with 3 divided by 2, which is 1.5. So the average of 2 and 1.5 is 1.75.
Oh, wait. Yeah, now let me try to plug in that value. Let's see if I was doing something right. Let's plug in 3. We have z running like that. Wait, it got into an infinite loop. Why? I am incrementing z here and it's turning. Oh, hell no. Hell no. Wait. Let me go back to how my previous solution was. Yeah. this is how it was. Very perfect. Z times Z minus X, and then we run this a bunch of times. Okay, run. That's what we had, but let's go for 3. Not available. Okay, back to the video.
We then do this exact same thing again, except we plug in 1.75 for x in instead of using 2 like we did for the first time. This results in the next iteration being the average of 1.75 with 3 divided by 1.75, which is 1.732. Carrying that out for a few more steps shows us the square root is approximately 1.7320508. That is, of course, the correct answer. So this equation works, but intuitively, why does it work? Well, it's pretty simple. If the guess we pick is smaller than the real square root, then a divided by x in will be bigger than the real square root. And so for our next step, the average between our guess and the result of that division will be bigger than the current guess. If our current x in is too big, then a divided by x in will be smaller than the real square root, causing the resulting average to decrease. This method also works for numbers less than 1. We can find the square root of 1/8 by initially guessing that the root is 0.5, and then working through the math to find that the root is approximately 0.3535. Sadly, this method can't directly be used for finding the square roots of negative numbers. Also, you can't pick 0 as your initial guess or the whole thing blows up.
Wow, and this guy only has where is it? Okay, I'm trying to understand what it is was done there. Trying to figure it out.
This is decrease. This method also works for numbers less than 1. We can find the square root of 1/8. Well, it's pretty simple. With 3 divided by 1.75.
So it comes by when you will guess that x of 0 is 2.0. Okay. I guess this is what we're trying to explain here. So a way to play with function, let us implement a square root function. Given a number x, we want to find the number z. Computers typically starting with some guess z. We can adjust z based on how close z square is to x. Producing a better guess. So if I plugged in 4, and I'm getting shit in the name of answers, so clearly I am doing something wrong. Don't wipe that. I think this is the same approach they're using here. Is it? What's the initial formula?
Square root of 3. Here, the a variable becomes 3.
So to get the square root of 3, this is the equation. So this xn plus 1 should stand like for our for loop, and we have half, I think, x of n, which could stand for the iteration number, which is like the number we are trying to plug in, and x of n here. And x of n here is like our guess.
Find the square root of 3. Here, the a variable becomes 3, and that will remain unchanged for every iteration. Now we need to pick a number that will be our starting approximate answer. We can estimate or just make a flat-out guess. It doesn't really matter. A closer estimate will converge faster, but even one wildly off will still get there. Since we're going for the square root of 3, we'll guess that the answer is 2. 2 becomes the x in this equation. Really, it's x0 because this is the 0th iteration. Now we solve for x in plus 1. And that...
Okay, so let's get something straight. I like to have my things clear. So let's just say we have a guess, and we're going to give it something like 1. Our guess is starting 2, right? Like what is listed here. Our guess is 2. And the actual number that we have to actually look for it is x, which is clear. Okay, fine. Now we just make a random guess for it, and then we start iterating through, looping through. And let's say we have a number of times we want it to run, not 10 times. We want it to run like 5 times at most. Of yeah, 4 times at most. This one should start at 0. What next? And this is half into x. So we're basically taking z should be 0.5. So the formula just says it's 1 divided by 2 1 divided by 2 and then we have something like this xn here plus, so we have our guess, kind of our guess, plus I guess it's like that. Guess plus 3, guess plus x. Okay, so this should be in brackets. So our x now divided by x of n. I know I'm not following this exactly truly, because what I'm seeing here, okay, this one says z minus equal to, shit, I wasn't even reading here. Whatever. Okay, so back to this. I think this is the same formula that was used here. F the derivative of f of x. Okay, and then 3 divided by x of n divided by the guess. All of this should be under this bracket. Good. So we have x divided by the guess and that. And what we want to do is, are we printing? No. So do we need this again? No. So we just we have to convert this float 6 to 4 rather. The guess to be starting from 2. That's our guess. And then we are just plugging it. So this should be our guess. So I get, so this should be z. Definitely this should be z. Z. Yeah. That should be our z. We can wipe that out. And then we can then print z, return z. So I'm saying my guess number I'm starting from should be 1, right? And let's say we want to get the square root of 4. Let's run and see. Is it declared but not used? How is it not used? It should be plus equal to. Nah, how can square root of 4 be 1? Okay, wait. Let me cook. God damn. So let's put 2 there. And square root of 4 is 2. Square root of 3, 2. What's happening? So we want to print Z. Ah, yeah. I think this is it. Okay. Let me create another variable and call this u, and then I just want it to print out u like this. Yes, I know this variable will only be accessed inside there. 1.75 is running the same iteration over. Next time it's supposed to run, it's supposed to plug in 1.75 back into the equation, because this is it here. We have it working in his example.
Just want that out for a few more steps.
So when it goes 1.75, after running the first iteration, we're gonna replace it in 1.75, and the resulted answer is 1.732, divided all by the same stuff. So if I'm doing that, so the next time it's running, it's still running the same z. Okay. Let me check something inside my source code here. To replace an existing variable is like, yeah, so I can reassign. So let me reassign after printing out every value. Let me reassign the value. So let's say z now is going to be u. Does that work? Hopefully the data type 2 runs quite well. Exactly, fantastic. So we have 7.3, perfect. So we have 732
divided by 1.7. Square root is 1.732.
and I have the last iteration is
that is of course
732508, and yeah, and you notice the position becomes like something is like consistent here now. So 732508. Okay, so fantastic. So that's like the square root. So assign it a new value and then we are printing it over and over. Okay, so square root of 4. Let's plug in 4 and watch it run. Sensational, my bruv. Sensational. 5. Let's do 5 now. Is it actually 2.2? Like, where's my calculator? Where is it? Let's go back. Calculator. Square root of 5, my nigga. Ah, wow. Lovely stuff. 2.236 something 75-ish. Yeah, so these values here have been stripped out and being dropped to 5. Perfect. So I don't know if I reduce the number of iterations to like something like 3, it actually stops it from happening. I can remove this printout statement here, remove this too, because I guess it's printing out so many freaking times. Yeah, that's it. Not bad. guess this is another way to approach the situation. I'm guessing this is the same thing. Like, it's definitely the same thing. Is it? Yeah. Because this is z times z. Like, it's our guess. We are taking 2 times 2 minus the real number we're trying to guess. So let's say 2 times 2 is 4. Let's say we're trying to get the square root of 4, right? Let's say we're trying to get the square root of 4. So we have our z will be equals to, we are just saying it will be 2 times 2, like that, minus our x, which is 4. And we are simply dividing all of that garbage times 2 again, times 2 again, and this times 4, isn't it? No, our guess is 2. Yeah, I guess it's 2. So we have up here 2 times 2, which is 4. 4 minus, oh hell no. Wait. So if we're taking 4, we're assuming that the square root of 4 is but this thing, I think this statement has a clue, because it says repeating this adjustment makes the guess better and better until you reach an answer that is close to the actual square root as can be. Implement this in a function square root. A decent starting guess of z is 1, no matter what the input. To begin with, repeat the calculation 10 times and print each z along the way. See how close you get to the various values of x of 1, 2, 3, and how quickly the guess improves. To hint, to declare and initialize a floating point value, give it floating point syntax or use a conversion. Next, change the loop condition to stop once the value has stopped changing. Okay, so change the loop condition to stop once the value has stopped changing or only changes by very small. See if that's more or fewer than 10 iterations. It's nice. Okay, to make it stop, especially when the values are clear, are getting smaller or bigger, because I think if I start putting square root of 10 here, this number of iterations will not give me something accurate. Non-declaration inside or outside body. But if I were to run this 10 times and I was actually fmting and printing the line of my u like that, I think I was getting excellent results. So print f line u, run. So the precision starts changing. Okay, so I can just do a small if condition here. I just say if u is greater than, no, if u is equal to, because I think there are some places where it stops changing completely. Yes, when it becomes equal to, I want you to go back to the previous iteration, to the last answer. Because if it starts this, it will go here, this 3.5, it goes this, this. We have to check if this guy is equal to this guy. If he checks that it's not equal to, or the difference, if I try to subtract this, let me see how the answers will be. So if I was to put something like this, something copy. I'm not even ready for all this rubbish. Classic. Okay, let's close that. So if I say this is this, so I have 3 point that minus this. What will be the answer? Excuse me. Wait. Let me refresh myself again. Five minus 3, 2, and then 3.16. Okay, 3.5 minus definitely there should be some significant difference. 0.3. Okay, now if this difference between the two, .7. I really don't know why I'm doing all this. I just really want to get as close as the tutorial is asking for. So 0.01. So when you subtract that, now when you subtract, I think if you just put this and subtract from this guy, you should get the difference. Not really. I think it's this minus this legend down here. .004. Okay, so definitely if it starts reducing, the precision is reducing. So I'm just going to return the last. Okay, so I'm just going to return the last. So if u is equal to z, right? We should just return. I think returning inside here should just break the loop. So just return z. Okay, so let's run. Undefined u, yeah. Run. Now there are lots of print statements, so I don't know which one got printed out first. So this is 1, 2, 3. Say 1 3 times the 4th time. I think the last time he ran 10 times, so this one actually stops it. So let's put let's say 100. Square root of 100 is, I think it's 10. It should run once. The freaking square root of 100 is 10. Oh, am I wrong? Like, yo, what's happening? Square root of 100, like blood, 10, and I'm seeing these misconfigurations here. Like, what the freak? Where is 26 printed out from? Okay, the precision, like, so definitely starts from 14, 10, 10, 10, 10, 10.00, then finally becomes 10. Wow, that is great. I didn't scroll down. Okay, so 1000. So definitely the square root of 1000 is 100. No, sorry. A square root of 1000 should be of 1000. There's no square root for 1000. I think the square root of 1000 should give us decimal points. Perfect. That's 1.62277. Okay, cool. All right. So I think we can modify this program to not have a specific number of iterations and so on. But I get it. It was fun exercise to, like work with the Newton-Raphson's equation. But honestly, right here, I wasn't understanding anything. Like, but now this makes sense because of this statement repeating the adjustment. Okay, so let's go ahead. Switch. A switch statement is a shorter way to write a sequence of if and else statements. Okay. So let me just type it out for myself. So switch was, so import runtime dot rules. What the hell is that? Okay, so it's like a method that tells us which operating system is being run. So I'm guessing OS is like the return statement. And then you have case, Darwin, fmt print. Cool. Let's see how it runs. Go runs on Linux. So default OS. Interesting. Another important difference is that all switch cases need not be constant, and the values involved need not be integers. Interesting. Switch cases evaluate from top to bottom, stopping when a case succeeds. So it reaches here, it succeeds, it just goes down. Yep, good evening. Okay, so most likely they've switch. So this is like assigning a variable and calling this variable and checking here along the line, which is something you can still do outside of the scope like it was done here. Okay, today time.now.weekday, switch time.saturday. It starts checking which one fits time.saturday. And these ones are just integers, so switch and compare with this. Defer. Okay, so defer is like holding on to an instruction until one instruction has been printed. So even I was to do another FMT, so what will happen if I do FMT, the print and hello world bang before the FMT. So hello world bang obviously normally will be printed, but when it reaches the defer statement it keeps it world. Okay, so if I move this bang from here, what you expect is hello world bang and world. Perfect. Okay, that's cool. That's a cool feature. Why do we even use this? I don't know. Defer functions calls are pushed onto a stack. Okay, when a function returns, it deferred call stacks. Its deferred calls are executed in last in first out order. To learn more about defer statements, read this blog post. Defer, panic, and recover. Go has the usual mechanism for control flow. If for switch go to, it has the go statement to run code in a separate go routine. Here I'd like to discuss some of the less common ones: defer, panic, and recover. A defer statement pushes a function call onto a list. The list of saved calls is executed after a surrounding function returns. Defer is commonly used to simplify functions that perform various cleanup actions. For example, let's look at a function that opens two files and copies the content of one file. Yeah, this will be obviously useful because sometimes you can run into they call it deadlocks. So two processes in the computer are accessing the same file. So I think it's quite possible. It's quite possible that can happen. I haven't even checked my chat. Hello to anyone who has joined. And welcome to the stream. Ooh, let me see my stats. Okay. Okay. Cool. Now, like I was saying, Go has a coroutine, blah 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 blah. So like this is very quite useful for if you're using with a, go to a deadlock with two processes because two files cannot be accessed by the same process at the same time. So this is definitely useful. That is nice. So srcl open file. If error is not equals to nil, return defer src close dst os.create dst name. If error, so if there is an error, open this file, something happens, this defer statement is there to close the file properly. So this one is like a copy file function. So the works by, for example, let's look at a function that opens two files and copies the content of one file to the other. This works, but there's a bug. If the calls to os.create, so os.create file fails, so this file, if it creates fails, the function will return without closing the source file. Okay, the function will return, yeah, definitely, without closing the source file, the source file. This can be easily remedied by putting a call to src.close before the second return statement. So we put this src close file. So yeah, defer, close the source file, and just keep it waiting. So before this one gets run into the instructions, first the stack is being called, the last one out, the last in, the first in, last out. So therefore, different statements allow us to think about closing each file right after opening it, guaranteed that regardless of the number of return statements and functions, the files will close. The behavior of the DF defer statement is straightforward and predictable. There are three simple rules. A defer function's arguments are evaluated when a defer statement is evaluated. Most of these things kind of make sense when you're actually working on the project itself. Like when you're not working on a project, it's hard to, kind of work or diversify something inside. So I'm going to obviously try this with a project in Go. Yeah, I'm going to try this with a project in Go and see how defer statement can use defer, panic, and recover. But it's a good thing to know about that something like this exists. Like to keep a function waiting. So like with this for loop, you can defer. This will defer like 10 times, and then before start printing the item. So print done first, and then starts the countdown. 9, 8, 7, 6, 5, 4, 3, 2, 1. Perfect. That is cool. Quite cool. And it's like a stack. Like as they come in, the last person to enter will be the first person going out. Congratulations, you finished this lesson. Let me go to the list of modules. So I think I'm done with this. I think what's left for me now is to do brush up on packages, variables, and functions. Packages, variables, and functions. Next lesson. Excuse me, you're taking me to pointers already, my friend. I just saw packages, variables, and functions. Okay, so let me go through this one quickly. Yeah, I'm aware about the imports. So this code group imports to parentheses, but I always recommend importing this. You have 2.6457531. Okay. Exported names. So in Go, a name is exported if it begins with a capital letter. For example, pizza is an exported name as is pie, which is exported with a math package. Pizza and pie do not start in the capital letter, so they are not exported. When importing a package, you can refer only to its exported names. Any unexported names are not accessible from outside this package. Run the code, notice the error, fix the error, rename math.py. So run the code, says math.py not found, you can rename this shit. Okay, I already did this already, so that's why it's showing. But if I were to put a small p, so if you want to export a function, if you put it in small letters, it won't work. So if you don't want a function to be exported from a module, you just simply don't make it a capital letter. But if you want to be use it outside of the scope of a module, that is actually very, very useful. Almost like things like private and public functions. That's quite useful. Okay. Let's go to 4 functions. A function can take 0 or more arguments. In this, R takes 2 parameters type int. Yes, I've seen this already. We can even wipe this out and just make it like x and y. I like this feature of Go. Yeah, this thing will still give us the same results. 55, even when I still specified and put int here like that. It will still understand that all of these types is because all of them are sharing the same data type, so there's no need to specify do x, y. It's clean, it looks neat. Yeah, and I've read this article already. Functions continue. When 2 or more consecutive name functions per share type, yeah, that's what I was just saying. Multiple results, function can return. I think I've done this already. yeah, I'm done with this already. Yeah. Okay, so go as pointers. A pointer holds the memory address of a value. So I am guessing with this particular one, I would really wish to read more again on pointers. I just want to understand pointers on a lower level. Yeah, and I think this guy, the low level learning, kind of like gave a very good explanation of what a pointer really is. I think he did a great job with that, explaining what a pointer is and how it works. So I'm going to just try it out again. Look.
Memory, you need to know how
2 years ago.
Pointers. Something about this concept just drives people crazy. And if you're a new programmer, well, you're not alone. I was one of those people when I learned C back in the day, and like you, I was eager to understand. In this video, I'll show you what a pointer is so you can fully understand how they work, the syntax of pointers, you can easily read them, and finally, why everyone cares so much about pointers and what they're used for. Before we start, if you're new here, hit that subscribe button, and while you're at it, leave a like. I put out videos demystifying topics like this and much more on a weekly basis. What is a pointer? The question that's been asked since the beginning of time. Well, maybe not that long, but computer science students have been asking this question for a while. Pointers are not that complicated, and let me show you why. To understand what a pointer is, we need to first understand how memory works. So here, I've laid out an example of memory. Memory in our example has two features, an address and a value. The address is the location of the memory, meaning where that memory is the data stored at that location, meaning what memory lives there. So for example, if I put a 4 here, what does that mean? All that means is that the value 4 lives at location hex 1000. Easy. And the notation in C, for example, may be int x equals 4, which gets allocated to that memory on the stack, and now that number lives there. So what happens now if at another location, I put the number hex 1000 at address hex 1004? I've just created a pointer. You may be thinking, low-level learning, how is this possible? That's just a number at a location. Well, guys, that's the secret. A pointer is just a value that happens to be an address. Mind blown. By setting the value of one variable equal to the address of another, that variable now points to the other. For new programmers, though, most of the time, that isn't as easy as it seems. One of the most common issues new programmers have with pointers is the syntax used to create them. The combination of stars and ampersands and arrows and more stars creates a lot of confusion, so let's break this down using our previous example. In our last example, we made an integer x whose value was 4 at location hex 1000. After that, we made a pointer that lived at address hex 1004 whose value was hex 1000. So how do we do that in C? We could do that using 2 lines of code, and I'll break them down part by part. The first line is int x equals 4. This line is pretty straightforward. The first part, integer, is the type of the variable, which is 4 bytes wide, and this will matter later in the video. The second part is the name. Nothing special here, just the variable name x. And then after that, we put an equal sign, which when describing C, we can verbalize the equal sign to is set to. And then finally, the value 4. So the final sentence we've come up with is integer whose name is x is set to the value 4. Okay, easy part over. Next is the hard part. To make a pointer to x, like we did in our example, I would say the following line of C. Int star px is equal to ampersand x. Now, I know that sounds pretty crazy, a little scary. Let's break it down piece by piece. From left to right, we can see the type again, starting with int. But next, we see the dreaded asterisk. What does that mean? When an asterisk is placed next to a type, it modifies the type, meaning that our variable is now a pointer to an integer. So our variable here points to a 4-byte value. Next, the variable's name, which is px or pointer to x. You can name it whatever you want, but this is a good habit, using p to denote that it's a pointer. And then after that, our equals sign, which again means is set to. And then the next dreaded character, the ampersand. Whenever you see an ampersand, just think in your head, the address of. So this means the address of x. Our final sentence here is int pointer px is set to the address of x. So what does this do for us? Well, now by using the pointer, we have a way of accessing x by reference instead of by value. So for example, if we wanted to copy the value of x to a new variable using that pointer, we could do that pretty easily with this new bit of code. We'll say that int y equals star px. Now, what is this code doing? Let's break it down. Again, y, just like x, is a normal integer, so no pointers yet. We say that y is set to, using that equal sign, the asterisk again. Remember how last time I said when we see an asterisk, it's used to modify a type if a type is near it? Well, here there is no type. When it's used alone this way, the asterisk is referred to as a dereference. The dereference means go to the address pointed to by the pointer and grab that value. So because px points to x, the dereference will go and grab that value and it will set y equal to x. So when we're verbalizing C, when you see an asterisk by itself, you can say the thing pointed to by. This would mean that the final verbalization of this line of C is integer y is set to the thing pointed to by px. By doing this, we can pass around x by reference instead of value, and why that matters I'll explain in the next part of the video. The final concept that confuses people the most when learning about pointers is, why does anyone use them? The syntax is confusing, my programs crash all the time when I use them, why does anyone bother? Well, the answer is because we have to. To avoid making code that is impossible to read or unscalable, we break down functions based on the action that they perform. So here I have a small snippet of C where I have a function that updates the age of a person structure. The problem is that the structure I'm editing is not in scope of the editing function. To get around this, we pass the struct by reference so that now the pointer to the structure is in scope of update struct and can therefore be edited. Using pointers like this keeps our code clean and understandable while reducing the amount of space that we use by not copying. Another reason that pointers are inevitable when coding in C is the idea of using static versus dynamic memory allocation. Static allocation is typically a variable that goes onto the stack, a place that is always in scope for the function that is running it. However, when you're using dynamic allocations that come from the heap through malloc or sbreak or other kinds of memory allocators, you are going to get a pointer to memory that is out of scope. If you ever want to be able to use this kind of memory, you need to know how pointers work. The primary difference between dynamic and static allocations is that static allocations are things that are known to have a fixed size at compile time, whereas dynamic allocations can be changed in.
This is good. This is why I think I will have to start the series of doing my data structures and algorithm too. Studying in C, learning my data structures and algorithm. So I think I will just add that. So just stay tuned for that. I will most likely add my data structures and algorithm in C too. And don't forget, I also do the VODs too on YouTube. Yeah.
Size as the program runs. Here you see I allocate a string of 100 bytes to be pulled from the heap, but that 100 bytes could have come from a user input or something else. If you're having a hard time with C, don't be discouraged. Pointers do take a minute to master, but once you get them, you'll know it and you'll feel like a real low-level wizard when you do. Guys, I had a
Okay, so that was pointers in a crash course. So I am going to continue this. Right now I need to go do something else, but I am going to continue up my work with Go, and then after that I'll start working on the project in Go, getting used to the runtime, building stuff with it. So I hope I'll see you guys in a few hours. Just want to wrap up something. So this is me learning Go. Don't forget to also to subscribe to, for those for my users, especially on Twitch. Don't forget to follow, and also on YouTube. Don't forget to subscribe and hit the like button. Okay, see ya.